moving through space and numerous stars distributed across the night sky. However, significant cosmic phenomena occur not only in the plane around us, but also in the dimensions above and below it. Powerful gamma-ray bursts are directed toward the galactic north, while gravitational forces influence our cosmic trajectory from below. These elements demonstrate that the solar system exists within a multidimensional structure with vertical extents that are still being explored. A common view of the universe is the arc of the Milky Way, with its stars spread across the night sky. Astronomers refer to the galactic North Pole, a direction extending outward from our galaxy's plane that provides an unobstructed line of sight into distant space. This northern pole has historically received significant attention due to its clarity and the visibility of numerous ancient galaxies. The universe, however, has two sides. Corresponding to the north is a south pole. The galactic South Pole offers a perspective that is equally valuable and significant. Observing toward the galactic South Pole provides another cosmic viewpoint that helps create a balanced model of the universe and an understanding of the Milky Way from above and below. The galactic South Pole is a precise location in the sky situated within the constellation Sculptor. This faint group of stars was first catalogued by the French astronomer Nicolas Louis de Lacaille in the 18th century. While the constellation is not prominent, it contains a clear view into the far reaches of the universe. To visualize its location, the Milky Way can be conceptualized as a large rotating disk with spiral arms composed of billions of stars, gas clouds, and dust streams. Two poles, a north and a south, extend from this disk. The galactic South Pole is located at an angle of exactly 90 degrees below the plane of the disk, positioned as the direct opposite of the galactic North Pole within the coordinate system used by astronomers to map our galaxy. Although the North Pole is frequently the focus of research conferences and public attention, the South Pole holds equal importance. Without it, astronomers would have a one-sided view of the galaxy's symmetry. By comparing the north and south, they can determine if the Milky Way is balanced, if its halo of stars and dark matter is spherical, or if one side has been shaped differently over time. From Earth, the galactic South Pole is most clearly observed from the southern hemisphere. Observers in locations like South America, Africa, and Australia have the optimal position for its study. For those in the northern hemisphere, this pole remains below the horizon and is therefore not visible. This southern region of the sky is like its northern counterpart, relatively quiet. In astronomy, a quiet area is one that is not obscured by nearby stars, glowing gas, or dark interstellar dust. The central part of this polar region is notably clear. For astronomers, this clarity is advantageous, as a quiet field offers an unobstructed window into the deep universe. This allows for the observation of large-scale cosmic structures beyond the Milky Way, such as galaxy clusters, vast filaments of matter, and the large dark voids between them. The galactic South Pole has been a preferred region for astronomers aiming to map the universe in 3 dimensions. Among the most notable of these initiatives was the 2-degree Field Galaxy Redshift Survey, 2DFGRS. This project, conducted during the late 20th and early 21st centuries, measured the distances to over 200,000 galaxies. The galactic South Pole was selected for this large-scale survey due to its clarity. The region has minimal intervening dust or gas, resulting in very low extinction, which means the view is not significantly blurred or dimmed by material within our own galaxy. This characteristic makes it one of the best available cross-sections of the universe for astronomical observation. By analyzing the galaxies visible beyond the South Pole, scientists produced some of the first extensive maps of the universe's large-scale structure. These maps show that galaxies are not distributed randomly in space, but are arranged in vast chains and sheets separated by enormous voids, a structure known as the cosmic web. The galactic South Pole provided one of the first perspectives through which this grand design was observed, while the view outward through the South Pole reveals the universe beyond it, also provides information about our own galaxy. By observing how the density of stars and gas decreases with distance from the Milky Way's central disk, astronomers can determine the shape of the galaxy's halo, which is the large, faint sphere of stars and invisible dark matter surrounding the disk. A comparison of data from the North and South Poles is a particularly effective technique. If the Milky Way were perfectly symmetrical, the two poles would appear identical. Research, however, indicates this is not the case, with the southern view suggesting asymmetries. These irregularities may be residual effects of past galactic collisions. Over billions of years, the Milky Way has grown by absorbing smaller galaxies. The stars and dark matter from these assimilated systems leave behind faint streams, ripples and clumps that are more easily detected through the clear line of sight offered by the South Pole. Consequently, the galactic South Pole serves as a form of historical archive, containing evidence of the Milky Way's formation and growth. The galactic South Pole also functions as a practical resource in modern astronomy. Numerous space observatories use it as a calibration field to check and adjust their instruments for accurate measurements. Telescopes such as GALEX, ultraviolet, Spitzer, infrared, Chandra, X-ray, and Planck, cosmic microwave background, have all utilized the galactic polar regions for this purpose. Because these areas are relatively free of foreground objects, they are ideal for testing instruments against faint and distant signals. The Planck spacecraft, for example, used the galactic poles to refine its measurements of the cosmic microwave background, the residual radiation from the Big Bang. Such precise observations would have been extremely difficult without the clear views provided by the galactic South Pole. The region of the galactic South Pole is also host to two of the Milky Way's nearest companions, the Sculptor Dwarf Galaxy and the Fornax Dwarf Galaxy. These small galaxies orbit our larger galaxy and are of immense scientific value despite containing relatively few stars. As these dwarf galaxies are dominated by dark matter, their study helps astronomers test and refine models of galaxy formation and evolution. By tracking the motion of stars within Sculptor and Fornax, researchers can measure the gravitational influence of invisible dark matter. These measurements provide insights into how the Milky Way has accumulated mass over billions of years. Sculptor and Fornax are analogous to ancient systems that retain conditions of the early universe, and their proximity to the galactic South Pole enhances the region's importance. The South Pole also coincides with an area called the South Galactic Cap, a high-latitude region that is a frequent target for deep sky surveys. Just as the North Galactic Cap has been used to identify large filaments of galaxies and vast cosmic voids, the Southern Cap provides a complementary perspective. A complete three-dimensional map of the universe can only be constructed by combining surveys from both the northern and southern regions. A map missing one half would be incomplete, similar to attempting to understand global geography while neglecting an entire hemisphere. The galactic South Pole helps ensure that our mapping of the cosmos is comprehensive and accurate. In recent years, the study of gravitational waves has emerged as a new field in astronomy. These waves are disturbances in space-time, generated by cataclysmic events such as the collision of black holes or the merger of neutron stars. Projects like LIGO in the United States and Virgo in Europe have detected numerous such events, confirming predictions made by Albert Einstein over a century ago. Future observatories, including the space-based mission LISA, will continue this research. For gravitational wave astronomy, the polar regions of the galaxy are highly valuable because they remain visible for extended periods, which permits continuous monitoring of potential events. The galactic South Pole serves not only as a visual window, but also as a listening post for the universe's fundamental vibrations. It also helps to unravel the Milky Way's magnetic field. These fields, functioning as invisible lines of force, permeate the galaxy, shaping the movement of charged particles, directing cosmic rays, and affecting the flow of interstellar plasma. While most of these fields follow the galaxy's spiral arms, some curve into the halo above and below the galactic plane. By observing from the South Pole, astronomers achieve a vertical perspective, as if stepping back to see the entire structure in 3 dimensions. Mapping these magnetic lines is also essential because they create foreground noise that can interfere with the detection of faint cosmic signals. Through careful study of the magnetic fields at the galactic South Pole, scientists can build cleaner models to separate the whisper of the early universe from the background hum of our galaxy. In scientific language, the galactic South Pole is known as a control field. Researchers studying the universe need reference regions, patches of sky that are relatively empty and quiet, against which they can compare more crowded observations. The South Pole provides such a region. Using it as a baseline allows astronomers to test models of dark matter, density-refined measurements of baryonic acoustic oscillations, faint ripples in the distribution of galaxies left from the early universe, and confirm the reality of faint distant galaxy clusters. Without such a control field, many cosmological results would lack certainty. It is true that the galactic North Pole often receives more attention in news, especially concerning deep field images or cosmic microwave background studies, but the South Pole is equally important. Together, the two poles offer balanced symmetry and perspective. The South Pole is a mirror to the North, showing whether our galaxy is symmetrical or slightly skewed. It provides a second calibration point for our instruments, ensuring the accuracy of cosmic measurements. It also grants access to quiet regions of space where the universe can be studied in its purest form. Perhaps its most important role is to remind us that a single viewpoint is never sufficient. To truly comprehend the Milky Way, the cosmic web, and the universe's grand structure, we must observe in both directions, north and south, above and below, outward and inward. Imagine rising high above the solar system, far beyond Earth, the Sun and the planets to a vantage point, floating outside familiar boundaries. From this position, one is no longer tied to the spinning Earth or its curved horizon. In the silence of space, directions like up and down lose their conventional meaning in an endless blackness dotted with stars. Yet astronomers need a fixed direction, a stable marker that remains constant, regardless of their line of sight or distance traveled. On Earth, we use the North Pole, the South Pole, and lines of latitude and longitude for navigation. In space, the concept of the galactic North Pole fills this role. The galactic North Pole is not a star or a bright beacon, but an invisible, purely geometric direction in the sky that scientists employ as a cosmic compass. Though it cannot be seen, its importance is extraordinary as it allows astronomers to define which way is above the flat disk of our galaxy. To visualize this, think of the Milky Way as an enormous thin disk, like a record or DVD, but millions of times larger than our solar system, with billions of stars, gas clouds and dust streaks spread across its surface. If a pin were inserted straight through the center of this disk at a perfect right angle, one end would point upward to the galactic North Pole, and the other would point downward to the galactic South Pole. The galactic North Pole is situated in the sky, toward the faint constellation known as Coma Berenices. It is not a famous constellation like Orion or Leo, although Leo is nearby. Coma Berenices is composed of dim stars that appear almost like a cloudy patch. Yet in that quiet area of the sky, astronomers have anchored one of the most significant reference points in all of space. Unlike Earth's pole, which shifts over time due to the planet's wobble, the galactic North Pole is fixed in a way that feels eternal. While the Earth may tilt, the galaxy's frame remains steady, providing the ultimate up of the Milky Way. The reason this is so important, even without gravity to define it, is that the universe is highly structured. Galaxies, spin stars, form in vast clusters. Black holes influence their surroundings, and invisible gravitational currents shape the paths of galaxies. To measure any of this, astronomers require a fixed frame of reference. When scientists study the tilt of galaxies, the movement of our solar system, or phenomena like the Great Attractor, an enormous gravitational anomaly pulling entire galaxies toward it, they must be able to state that we are moving in a specific way, tilted at a certain angle, or pointing in a particular direction. Without a standard point, like the galactic North Pole, every measurement would be uncertain. Just as a pilot uses pitch roll and yaw to describe an airplane's orientation, astronomers use three-dimensional directions anchored by the galactic North Pole to describe the orientation of the solar system. To establish this point, astronomers created the Galactic Coordinate System, which operates similarly to Earth's latitude and longitude. The disk of the Milky Way acts as the equator. The galactic North Pole is defined as the point at 0° circumlongitude and plus 190 circumlatitude in this system. Its mirror opposite the galactic South Pole is at 90 circ. When astronomers point their telescopes in this direction, their view becomes remarkably clear as the dense clutter of stars, gas and dust of the Milky Way's main disk falls away. The telescope's gaze instead passes through a much cleaner window of space, making the galactic North Pole one of the best locations for deep observations. Through it, astronomers have seen some of the most distant galaxies known. Light that has traveled for billions of years streams through this opening, reaching our instruments without being absorbed by our galaxy's dust. By observing through this direction, scientists have also mapped the halo of the Milky Way, a vast ghostly bubble of dark matter, thin gas, and scattered ancient stars extending far beyond the spiral arms. The halo is invisible to ordinary sight, yet contains much of the galaxy's hidden mass. Charting this faint structure would have been nearly impossible without the clear path offered by the galactic North Pole. The utility of this cosmic compass does not end there. The galactic North Pole also provides one of the best vantage points for studying the cosmic microwave background, radiation, the faint glow left over from the birth of the universe. This radiation, which fills all of space, is the cooling afterglow of the Big Bang, the event that began the universe nearly 14 billion years ago. To study this delicate signal, scientists need quiet regions of the sky, not filled with the noisy radiation of stars, dust, and gas. The Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck Observatory both turned their instruments toward the galactic North Pole. For this reason, Looking there is like peering back across almost the entire history of the cosmos to a time when the first atoms were forming and light was just beginning to travel freely. Even newer sciences, such as the study of gravitational waves, rely on knowing the galaxy's orientation. Gravitational waves are ripples in space-time created when massive objects like black holes or neutron stars collide. Detectors on Earth, such as LIGO and Virgo, record the faint tremors from these events. To make sense of the signals, astronomers must know their exact location within the galactic frame. These violent events are not scattered randomly, but cluster in regions of great mass, following the invisible structure of the cosmos. By mapping their positions relative to the galactic north and south poles, patterns emerge that would otherwise remain hidden. Meanwhile, our solar system is not fixed. The Sun, with its planets and comets, travels in a slow orbit around the center of the Milky Way, a journey that takes roughly 230 million years to complete. The Sun has orbited the galaxy fewer than 3 times since the era of the dinosaurs. As the solar system moves its orientation to the galactic North Pole changes, this journey is a slow, continuous circling among the stars. Knowing the location of the galactic North Pole today enables scientists to trace the solar system's past positions and predict its location millions of years in the future. This invisible point, which can only be identified through mathematics and precise definition, serves as a powerful reference. The galactic North Pole is not luminous, but it is essential for orientation. It functions as a silent navigational point for measurements and observations. This leads to the question of what exists directly above the Sun's North Pole. If one were to travel straight upward past the Sun's corona, the planetary orbits and the distant cloud of comets at the solar system's edge, one would enter immense open space. No physical wall edge or ceiling would be found. This space contains distant galaxies, quasars, and webs of matter that stretch across billions of light years. Each region would correspond to an earlier period in the universe's history. Throughout such a journey, the galactic North Pole would remain a directional marker. High above the Sun's turbulent surface lies the solar polar region, a mysterious and powerful area. This is not an empty or quiet space. It is active with invisible forces, where the Sun's magnetic fields bend, twist, and stretch. It is also a region where streams of hot charged gas called plasma constantly shift and flow outward. The Sun's equatorial region, by contrast, exhibits different phenomena. Their dark patches, known as sunspots, appear and fade, and violent explosions called solar flares erupt. The Sun's poles are quieter in comparison, but they are not inactive. They function like engines that powerfully shape the environment of the entire solar system. The effects of events that occur above the poles extend outward, influencing the space occupied by every planet, comet, and Earth. The Sun has a natural rhythm called the solar cycle, which repeats approximately every 11 years. During this cycle, the Sun's magnetic field becomes tangled and chaotic before it reorganizes, reversing its north and south poles. One of the calmest moments in this cycle is the solar minimum, a quiet phase when sunspots nearly disappear and the magnetic field becomes more orderly. At the poles during the solar minimum, the magnetic field lines straighten and extend outward into space. From these poles, streams of high-speed particles known as the solar wind travel across the solar system. These particles contribute to the formation of the heliospheric current sheet, a vast warped spiral of magnetic influence that extends from the Sun and envelops the entire solar system. This large invisible structure originates in significant part from the winds flowing from the solar poles. In 1990, the Ulysses spacecraft was launched to explore this region. It was the first mission designed to travel over the Sun's poles rather than circle its equator, providing the first view of the Sun from this angle. Throughout the 1990s and early 2000s, Ulysses completed several journeys over both the North and South poles of the Sun. Its discoveries were significant, revealing that the winds above the poles were different from those near the equator. At the poles, the solar wind was faster, thinner, and more steady. In contrast, the winds near the Sun's equator were denser, more chaotic, and changed speed and direction unpredictably. This fast polar wind is a key force that shapes the heliosphere, the large bubble surrounding our solar system. The heliosphere acts as a protective shield, deflecting the most dangerous cosmic rays originating from deep in the galaxy. Without it, Earth and the other planets would be exposed to much higher levels of harmful radiation. The heliosphere is a life-preserving environment, and the steady winds from the poles help determine its shape. The space above the Sun's North Pole serves as a gateway from which streams of energy particles and magnetic waves launch into the galaxy. Following these streams past the orbits of Neptune and Pluto would lead to the edge of the heliosphere, where the Sun's influence diminishes and galactic forces become dominant. At this outer edge, solar wind particles are less numerous and weaker, and the Sun's magnetic field stretches into thin strands that interact with the magnetic fields between the stars. This is the boundary where the Sun's influence gives way to the larger forces of the Milky Way galaxy. In 2012, the Voyager 1 spacecraft reached this frontier. Launched in the late 1970s, Voyager 1 traveled for decades before crossing the heliosphere's boundary near the Sun's northern edge, effectively passing above the Sun's North Pole in a galactic context. Beyond this border lies the local interstellar medium, a thin medium of gas dust and high-energy cosmic rays. The Sun is currently moving through a part of this medium known as the local interstellar cloud. This cloud is slightly warmer and denser than the surrounding space and exerts pressure on the heliosphere, compressing it on one side and stretching it on another. Because the Sun is moving rapidly through the galaxy, the heliosphere is not spherical but has a teardrop shape with a blunt nose facing the direction of travel. This nose is tilted slightly upward toward the region above the solar system's midplane and near the Sun's North Pole. This tilt means that many phenomena, particles, and waves encountered by deep space probes originate from above the planet's orbital plane. The Sun's North Pole therefore points not only upward but also forward in the direction of the Sun's travel through the galaxy, leaving the heliosphere entirely. The view from above, the Sun's North Pole, would open into the wider galaxy. This direction offers one of the clearest lines of sight into deep space, because the path is relatively free of the interstellar dust that blocks and scatters light in other directions. This provides astronomers with a nearly unobstructed view of the cosmos. Instruments, such as the Chandra X-ray Observatory and the Planck spacecraft, have used this clear vantage point. By observing along this path, they have studied distant galaxies, measured faint radiation from the universe's origin, and tracked high-energy X-ray sources. The Sun's North Pole thus points toward some of the clearest lines of sight into cosmic history. Cosmic rays, the particles that travel across the universe, also show unusual behavior in this direction. Studies indicate that slightly more of them arrive from the galactic north than from other directions. This suggests that the region above the Sun may be shaped by undiscovered structures and energetic events. The space above the Sun's North Pole is a borderland where solar and galactic domains overlap. In this transition zone, the Sun's influence flows outward, while the forces of the Milky Way press inward, creating a frontier where the two realms meet. Some of humanity's spacecraft, including the two Voyager probes, have already traveled into this region. NASA is currently studying a potential interstellar probe, a spacecraft designed to leave the heliosphere and explore the interstellar medium directly. If built, it would likely travel in a northward direction, similar to Voyager 1. The path above the Sun's North Pole is therefore not just a scientific concept, but a direction of exploration that humanity has begun to follow, from the Ulysses mission to the extended journey of Voyager 1, and potentially to a future interstellar probe. Our exploration has consistently advanced outward through a northern corridor. Each step moves us farther from the Sun and closer to the expanse of stars beyond. To travel northward, above the Sun's plane, is to depart from the familiar patterns of our solar system and enter a domain shaped by the galaxy. This represents a journey from the known into the unknown, between our star and interstellar space. High above and hidden within the Milky Way's glow lies a mysterious structure unfamiliar to most people. Astronomers, however, have studied it for decades, seeking answers to questions that still remain unsolved. This formation is called the North Galactic Spur. To the naked eye, it appears as a faint feature across the northern sky, resembling a large dusty bridge suspended among the stars. The spur is easy to overlook at first glance. Unlike the bright band of the Milky Way, which is illuminated by billions of stars, this feature is difficult to see. In visible light, it is obscured by thick clouds of gas and dust that block its natural glow. Yet when observed with specialized instruments, like radio microwave and X-ray telescopes that detect invisible forms of light, the North Galactic Spur reveals itself. Viewed through these instruments, it becomes one of the most prominent features in the sky. The spur is not a small local dust cloud. It is enormous. In maps created with radio waves, it appears as a long, curving filament shaped like a large arc. This arc rises high above the plane of the Milky Way galaxy and curves back down, forming a sweeping loop. The structure appears to originate near the galactic center and extends outward across a vast part of the northern sky. Its shape is reminiscent of a single glowing brushstroke across the heavens. The spur's size is immense, stretching across dozens of degrees of the sky and covering a region larger than the Moon, the Sun, or many familiar constellations. Despite decades of study, astronomers continue to debate the spur's exact nature. Several competing theories exist. One popular idea suggests the spur is part of a superbubble, which is a gigantic shell of gas and dust propelled outward by the combined explosions of many massive stars. When large stars end their lives, they explode as powerful supernovae, releasing immense energy. If several such explosions occurred in the same galactic region, their combined shock waves could sweep gas and dust outward into a large arc. This process would leave behind a loop-like remnant, which we may observe today as the North Galactic Spur. If this theory is correct, the spur is a visible record of violent stellar events that occurred millions of years ago. Other scientists propose a different explanation that places the spur much closer to our solar system. According to this view, the spur may be a wall of the local bubble rather than a massive galactic shell. The local bubble is the region of space through which our solar system is currently traveling. It is filled with hot, low-density, electrically charged gas spread over hundreds of light years. This bubble was also likely formed by a series of nearby supernova explosions that happened relatively recently, perhaps a few million years ago. If this theory is true, The North Galactic Spur is a local feature, a nearby wall of gas and dust from recent events, not a vast galactic structure. A third possibility combines the first two theories. Some astronomers believe the spur could be a local structure and a galactic-scale feature superimposed on each other. If so, telescopes pointed at the spur are looking through multiple overlapping layers of gas and dust. Each layer could be at a different distance, moving at a different velocity, and shaped by different events. This potential overlap significantly complicates the problem, similar to sketching a mountain range through drifting clouds that can hide, alter, or create illusory features. Determining the spur's true shape and origin is equally challenging. The North Galactic Spur is not only an astronomical puzzle, but also plays an important role in highly sensitive scientific experiments. A significant achievement in modern science is the study of the cosmic microwave background, CMB. The residual radiation from the Big Bang satellites, like WMAP, and the Planck mission were launched to measure this faint signal with high precision. However, our own galaxy also produces microwave radiation that can contaminate the CMB signal. The North Galactic Spur is a major source of this contamination. Its strong polarized radiation creates foreground noise that scientists must carefully subtract from their data without accounting for the spur. The CMB patterns, which hold information about the early universe, could be misinterpreted. At one point, some researchers suggested that signals from the spur might be evidence of dark matter annihilation near the galactic center. Dark matter does not interact with light, but its gravity shapes galaxies. When unusual radiation was detected near the Milky Way's center, some theorized it could be from colliding dark matter particles. However, later studies showed that this radiation was caused by conventional structures like the spur. This demonstrated the critical importance of understanding our galactic environment, as misinterpreting a nearby object can lead to incorrect conclusions about the universe. The spur also provides a rare opportunity to study magnetic fields on a galactic scale. While magnetic fields are normally invisible, tiny dust grains within the spur align with the Milky Way's magnetic field lines. This alignment causes the dust to emit polarized light, which consists of light waves oriented in specific directions. By mapping this polarized light, astronomers can trace the otherwise invisible structure of the galaxy's magnetic fields. The study of these fields is extremely difficult, and the spur serves as a natural laboratory for this research. In this capacity, the spur is a crucial scientific tool, not just a cosmic curiosity. Even with current knowledge, the North Galactic Spur remains a mystery. It does not behave like a simple arc or fit neatly into existing models of the Milky Way at times. It appears to be a perspectival illusion, an oddly shaped dust cloud that looks like an arc when viewed from Earth. At other times, it seems to be a vast, powerful structure whose true form is only beginning to be understood. The reality may be more unusual than any current theory, as the universe often presents surprises. Future missions with advanced technology may help solve this riddle by providing three-dimensional maps of the sky with unprecedented detail. The Sphere X mission is one such example. With these instruments, scientists may be able to measure the spur's true distance, trace its actual shape, and determine its origins. They might find it is a nearby wall of the local bubble, the remnant of ancient supernovae, or something entirely unexpected. Until then, the North Galactic Spur remains a dust structure stretching across the northern sky. It contains mystery history and the echoes of galactic events that occurred long before humans observed the stars. This faint arc across the Milky Way prompts consideration of the massive stars that may have created it, the cosmic gas bubbles that might surround us, and the magnetic fields, radiation, and secrets contained within its light. In the northern sky, far beyond Earth's atmosphere, exists an unseen but significant point known as the North Celestial Pole. It is not a physical object like a star or planet, but is instead an abstract point or direction in space. For millennia, this point has been fundamentally important for guiding sailors, explorers, and astronomers. Although invisible and intangible, the North Celestial Pole has influenced human navigation construction and scientific understanding for generations. The North Celestial Pole can be understood by visualizing Earth's rotation. The planet spins on an axis of rotation, an invisible line passing through the geographic north and south poles. If this axis were extended indefinitely into space, the point where it intersects the northern celestial sphere is the North Celestial Pole. From an observer's perspective on Earth, this pole is the fixed center around which all stars in the northern sky appear to rotate nightly. The apparent motion of stars, their rising and setting, is a direct result of Earth's spin. While stars seem to travel in circles, the North Celestial Pole remains stationary, serving as a crucial reference point for celestial navigation and astronomy. The star Polaris, also known as the North Star, currently marks the location of the North Celestial Pole. While not the brightest star in the sky, an attribute belonging to Sirius, Polaris is significant due to its position nearly directly above Earth's geographic North Pole. For anyone in the Northern Hemisphere, finding Polaris allows for the determination of true north. This made the star an indispensable navigational tool for sailors and land explorers before the invention of the compass. Polaris appears almost motionless, while other stars seem to circle around it, a phenomenon clearly visible in long-exposure photographs where stars form circular trails around a nearly stationary Polaris. This alignment is not permanent because Earth's rotation includes a slight wobble, a phenomenon known as axial precession. Similar to how a spinning top's axis traces a circle, Earth's axis completes a large, slow circle in the sky approximately every 26,000 years. This long-term cycle causes the position of the North Celestial Pole to shift, resulting in a change of the North Star over time. For instance, around 5,000 years ago, the North Star was Thuban in the constellation Draco, which may have been used by ancient Egyptians to align the pyramids. While Polaris is the current North Star, in about 12,000 years, this role will be filled by Vega in the constellation Lyra. Therefore, the designation of a particular star as the North Star is temporary. The North Celestial Pole's position is important for various activities. Astronomers use it as a reference to align telescopes for accurate tracking of celestial objects. Engineers utilize it for orienting satellites, calibrating spacecraft instruments, and aligning ground-based communication antennas. Precise measurements of the pole's minute shifts also allow for the study of gravitational forces from the Sun and Moon, which is information used for timekeeping, space mission planning, and climate studies. Furthermore, many ancient structures were aligned with the North Star of their era, and these structures now serve as historical records of the sky's changing orientation. The pole functions as a practical tool for navigation and science, linking human history with celestial mechanics. The North Celestial Pole serves as the pivot point for the apparent rotation of the night sky, caused by Earth's spin. While the constellations appear to rise in the east, move across the sky, and set in the west, over several hours the pole remains stationary. This effect is captured in long-exposure photographs, which show stars as circular trails of light. These trails all share a common center, which is the North Celestial Pole, currently marked by Polaris, visually demonstrating Earth's rotation around its axis. The concept of north extends beyond Earth. The solar system has a north pole defined by the Sun's equator, which differs from Earth's due to our planet's orbital tilt. The Milky Way galaxy also has its own north pole, located in the constellation Coma Berenices. Consequently, the up direction is relative and differs for Earth, the solar system, and the galaxy. To manage these different frames of reference, astronomers use three primary coordinate systems: equatorial coordinates based on Earth's rotation and the North Celestial Pole, ecliptic coordinates based on the Sun's apparent annual path, and galactic coordinates based on the Milky Way's structure. The North Celestial Pole is the fundamental reference for the equatorial coordinate system. The North Celestial Pole also serves as a sensitive instrument for scientific measurement. By tracking its slight movements relative to distant stars, astronomers can detect the gravitational effects of the Moon and Sun changes in mass distribution in Earth's oceans and atmosphere and the rate of melting ice caps. This precise monitoring of the pole's position contributes to the refinement of calendars, climate models, and the planning of high-precision space missions. Due to the long-term circular motion of Earth's axis, the celestial view from Earth changes over thousands of years, altering the positions of constellations and the appearance of seasonal skies. The sky observed today differs from that of the past and will differ from that of the future. The North Celestial Pole's movement is responsible for this gradual transformation of the celestial sphere over millennia. Observing Polaris is equivalent to looking along Earth's axis of rotation toward the sky's central pivot. While it has historically symbolized stability and guidance, its apparent fixed position is temporary, as the pole is in continuous slow motion. This creates a paradox of a seemingly permanent point that is actually part of a cycle lasting tens of thousands of years. The North Celestial Pole illustrates that even the most stable-seeming celestial markers are not eternally fixed, but are participants in cosmic motion. The common perception of the universe as a static, empty void with stars is inaccurate. Space is not empty. It contains invisible forces, streams of particles, and large, unseen structures. Among these phenomena, one of the most significant and mysterious is the magnetic field. Invisible to the human eye, magnetic fields are ubiquitous, guiding the paths of particles, influencing star formation and shielding planets from cosmic radiation. Earth is enclosed within a magnetic field generated by its molten core, without which life as we know it would likely not exist. Earth's magnetic shield, however, is one layer of a larger protective structure. Surrounding the entire solar system is an even greater shield known as the heliosphere. The heliosphere is a region of space created by the solar wind, a continuous invisible stream of charged particles that the sun emits in all directions. This constant outward flow fills the solar system and pushes against the material in interstellar space. Within this protective region, the sun's winds and magnetic fields control the environment, shaping the space through which Earth and other planets travel. Beyond this boundary, the sun's influence diminishes and galactic forces become dominant. At this boundary, the interstellar magnetic field, which belongs to the galaxy itself, becomes evident. The edge of the heliosphere is not a sharp, solid barrier, but a shifting, transitional zone where the outward-flowing solar wind meets the interstellar medium, the thin mixture of gas dust and magnetic fields between the stars of the Milky Way. In this interaction, neither force prevails. Instead, the solar wind slows, becomes turbulent, and halts at a border known as the heliopause. This marks the limit of the Sun's influence, where the solar wind can no longer push back against galactic forces. Beyond this line, particularly above the Sun's northern pole, the galactic magnetic field bends and twists through the region. In this frontier zone, solar and galactic forces interact. In 2012, the Voyager 1 spacecraft, launched in the late 1970s, reached the edge of the solar system, becoming the first human-made object to enter interstellar space. Scientists had expected that as the spacecraft crossed the heliopause, the magnetic field's direction would abruptly reverse, but this did not occur. Instead of a sudden change, Voyager recorded a gradual process where the solar magnetic field bent, twisted, and merged with the galactic magnetic field. This discovery demonstrated that the edge of the solar system is not a distinct separation, but a zone of integration between our Sun and the galaxy. The magnetic fields above the heliosphere play an active role in our solar system's dynamics. Cosmic rays, which are powerful particles originating from events like exploding stars and black holes, travel through space at nearly the speed of light. The magnetic fields at the edge of the heliosphere regulate how many of these particles can enter our solar system by either blocking, deflecting, or channeling them toward the planets. During periods of high solar activity, the Sun's magnetic shield strengthens, making it more difficult for cosmic rays to enter. When the Sun is quiet, its shield weakens, allowing the galactic magnetic field to push more cosmic rays into the solar system. Scientists have observed that many of these particles enter more easily from the direction of the galactic north. This is supported by data from the Interstellar Boundary Explorer, IBEX, and Cassini spacecraft, which detected a faint ribbon of energetic particles in the sky, aligned with the local interstellar magnetic field. This feature is a visible manifestation of the external forces pressing on our heliosphere. The discovery provided strong evidence that the Sun and its heliosphere are being compressed and shaped by surrounding galactic magnetic fields. Despite these findings, the precise shape of these magnetic lines is still not fully understood. Scientists are investigating whether these magnetic lines are smooth and uniform or tangled and complex. As a result of ancient explosions, the Milky Way's rotation, and stellar winds. The arrangement of these lines has a direct impact on space exploration, as magnetic fields can accelerate particles, trap them in radiation belts, disrupt spacecraft signals, expose astronauts to cosmic rays, and affect navigation systems. Measurements indicate that the magnetic field just outside the heliosphere has a strength of approximately 3-6 microgauss. Though far weaker than Earth's magnetic field, it is strong enough to shape particle flows and influence the heliosphere's structure. Some scientists theorize that our solar system is drifting into a new area of the local interstellar cloud with different magnetic conditions. If correct, the heliosphere's shape could change over thousands of years, altering its protective capacity against cosmic radiation and reshaping planetary environments. A possible link may exist between our local magnetic field and the North Polar Spur, a large arc of gas dust and magnetic activity rising above the galactic disk. Some researchers suggest that the interstellar magnetic field around our solar system may align with this structure. If so, our solar system could be situated within a galactic channel for the flow of particles, dust, and radiation, implying its position is part of a larger cosmic structure. To investigate these phenomena, new missions such as the Interstellar Mapping and Acceleration Probe, IMAP, are being prepared for launch in the late 2020s. IMAP's objective is to map how particles accelerate at the edge of the heliosphere and how the galactic magnetic field influences that process. Its advanced instruments are expected to reveal the shape and direction of the magnetic lines above the Sun, clarifying where our solar system ends and how it fits into the galaxy's magnetic framework. It is clear that the edge of our solar system is a dynamic boundary. The heliosphere provides protection, but is also vulnerable to galactic forces. The magnetic fields there are not static. They are shaped by stellar life cycles, the rotation of the Milky Way, and stellar winds. These fields influence cosmic ray trajectories and have implications for space travel. Space is not empty, and at the boundary where our star meets the galaxy, the magnetic field demonstrates our solar system's place in a larger cosmic context. When observing the night sky, attention is often drawn to the wide, bright band of the Milky Way from Earth. The Milky Way appears as a band of light composed of numerous stars. Astronomers recognize this feature as the flat disk of our galaxy, which contains stars, gas clouds, and dust. This disk, however, is not the entirety of the galaxy. A much larger and less visible spherical structure of matter exists above, below, and around this spiral disk. This faint and diffuse structure, known as the galactic halo, surrounds the galaxy like a transparent sphere. Although it is not visible to the naked eye, its gravity influences everything within the Milky Way, binding together its stars, gas, and our solar system. As the Sun and its planets orbit the galactic center, they travel through the lower part of this large and enigmatic halo, a structure whose properties are still not fully understood by astronomers. The galactic halo is composed of two different parts. The first is the stellar halo, which contains very old stars and many globular clusters. A globular cluster is a gravitationally bound, dense sphere of hundreds of thousands or millions of stars that have been orbiting the Milky Way for billions of years. Unlike the stars in the galactic disk that follow organized circular orbits, the stars of the stellar halo have elongated, tilted, and irregular paths that sometimes take them far from the galactic plane. Their movements indicate they are not native to the Milky Way. These stars and clusters are remnants of the galaxy's past, providing evidence that the Milky Way grew by absorbing smaller galaxies. The remnants of these consumed galaxies were dispersed throughout the halo, and each star, on an irregular, tilted path, is a survivor of these ancient collisions. The second and more substantial part of the halo is composed of dark matter. Dark matter does not emit, reflect, or interact with light, making it invisible to telescopes, yet it comprises more mass than all the stars, planets, and gas clouds in the galaxy combined. Astronomers estimate that over 80% of the Milky Way's mass is this invisible material. The dark matter halo extends hundreds of thousands of light years outward from the galaxy. Evidence for its existence is derived from its gravitational effects on stars. The Milky Way's spiral arms rotate faster than they would if only visible matter were present. This unexpectedly high rotational speed suggests a large amount of unseen mass is holding the galaxy together, a mass attributed to the dark matter halo. Our solar system resides within the lower part of this halo. This region contains rarefied gas, ancient stars, and the gravitational influence of dark matter. The density of this area is lower than the vacuum achievable in laboratories on Earth. Despite being so diffuse, the halo is critical to the galaxy's stability. It exerts a gravitational pressure that helps the Milky Way maintain its shape. The halo's gravity also retains small companion galaxies in orbit, preventing them from drifting into intergalactic space. In recent decades, astronomers identified an additional layer of the halo called the circumgalactic medium. This is a vast expanse of very hot gas surrounding the Milky Way. It is nearly invisible in optical light, but emits faint X-rays. It is detected indirectly through its interference with light from more distant objects such as quasars. The gas temperature ranges from about 1 million to 10 million Kelvin, and this medium may contain more matter than all the stars in the Milky Way. The gas is not distributed uniformly and is more concentrated above and below the galactic disk. Studying the circumgalactic medium is difficult as it cannot be photographed directly. Instead, scientists construct an understanding of it from indirect clues, such as its effects on radio waves, its light-scattering properties, and the absorption lines it creates in light from distant galaxies. To investigate this hot halo, astronomers use specialized space observatories. Satellites like Rosat Chandra and XMM Newton have been vital for collecting data on the hot gas. Future planned missions such as XRISM and Athena are designed to provide more detailed observations of this region. The halo is not a static environment. Located high above and below the galactic center are two immense structures known as the Fermi bubbles. These structures extend for tens of thousands of light years and are composed of gamma-ray radiation, the most energetic form of light. Their immense size suggests they were created by powerful events. The leading hypothesis is that they were formed by energy released from the Milky Way's central black hole during a past outburst, possibly after it consumed a large gas cloud or a small galaxy. The Fermi bubbles show that the halo is a dynamic structure that can be shaped by forces from within the galaxy's core. Our solar system is located within the galactic halo, orbiting the center of the Milky Way at a distance of about 26,000 light-years. This orbit is not flat, but oscillates up and down through the galactic plane, with one full cycle taking between 30 and 35 million years. During this time, our solar system travels through different parts of the halo with varying densities. Some scientists have proposed that these passages could affect events on Earth, potentially influencing the number of comets entering the inner solar system or contributing to long-term climate changes and mass extinctions. These ideas are not confirmed, but they suggest the halo may have a direct influence on Earth. The galactic halo contains a record of the Milky Way's formation. Its old stars and clusters document the cosmic collisions that built the galaxy. Its dark matter provides the gravitational mass that dictates the rotation of the spiral arms. The hot circumgalactic medium surrounds the galaxy, while the Fermi bubbles show evidence of eruptions from the central black hole. The halo also contains our solar system, binding it to the galaxy. It is a dynamic and essential archive of cosmic history that is fundamental to the galaxy's structure. Typical thoughts about the space above Earth are often focused on local phenomena like solar, wind, rogue planets, or cosmic dust. These objects are part of our immediate galactic neighborhood. However, shifting perspective to the scale of the largest structures in the universe changes the meaning of above. It is not simply the sky overhead, but encompasses a far grander scale than that of individual planets or stars. The universe consists of unimaginably vast structures, including collections of galaxies, enormous flows of matter, and invisible currents of gravity that shape the cosmos itself. Our solar system is a minuscule part of the Milky Way galaxy, a vast spiral of stars. The Milky Way, however, is not an isolated entity. Along with countless other galaxies, it belongs to a structure so enormous that it dwarfs anything visible to the naked eye. Astronomers call this giant realm the Laniakea supercluster, a name from the Hawaiian language meaning immense heaven, which is a fitting description of its scale. Laniakea is not a random scattering of galaxies, but a coherent cosmic structure where gravity has gathered matter. Much like rivers on Earth follow the contours of the land toward the sea, galaxies within Laniakea flow along invisible gravity-shaped paths toward regions of greater attraction. This supercluster is immense, stretching more than 500 million light-years across. To put this in perspective, light traveling at nearly 300,000 kilometers per second would need 500 million years to cross from one side of Laniakea to the other. This vast expanse contains thousands of galaxies, including our own Milky Way, all engaged in a shared journey. At the heart of Laniakea lies a mysterious gravitational anomaly known as the Great Attractor. It is not visible and emits no starlight, yet its gravitational influence is undeniable, acting as a cosmic center of attraction that pulls galaxies like the Milky Way Andromeda and others in the Virgo cluster toward it. The identification of Laniakea in 2014 was a turning point in astronomy. Previously, superclusters were defined by their visual appearance based on the light from their constituent galaxies. Laniakea, however, was discovered through the study of peculiar velocities, the subtle motions of galaxies independent of the universe's overall expansion. By measuring these relative drifts, scientists found that seemingly separate galaxies were connected through their movements, forming a single, vast gravitational flow. Laniakea's structure was thus outlined not by light, but by patterns of motion, dictated by gravity. From our vantage point, inside the Milky Way, much of Laniakea's mass is located above our galaxy's plane, extending into the northern sky toward constellations such as Virgo Centaurus and Hydra. Looking in these directions means observing the densest regions of our cosmic home. Astronomers have noted that the northern celestial hemisphere displays a more complex cosmic web than the southern one, as many major galactic flows are directed northward. This has practical implications, leading major observatories and surveys like the Sloan Digital Sky Survey and the Cosmic Flows Project to focus on the northern sky. The southern sky is more difficult to study because it is obscured by the dense band of our own galaxy. However, astronomers use clearer viewing areas or cosmic windows, like the North Galactic Cap, to peer past the Milky Way and map the large-scale architecture of galaxies and voids. Within Laniakea, astronomers have mapped vast cosmic filaments, which are long, thread-like structures where galaxies cluster. These filaments act as channels, guiding matter toward major gravitational hubs such as the Great Attractor and the enormous Shapley supercluster, which also lies within Laniakea's domain. The Milky Way is moving along one of these filaments toward the supercluster's northern reaches. Evidence for this motion comes from the cosmic microwave background, the faint afterglow of the Big Bang. A subtle temperature difference across this background, known as the dipole anisotropy, reveals that our solar system is moving toward the central mass of Laniakea, confirming our journey is a real and measurable phenomenon. Despite our growing knowledge, a full understanding of Laniakea remains elusive. Its boundaries cannot be captured by conventional telescopes because its structure is defined by gravity, not light. Mapping it requires not only powerful instruments, but also sophisticated models and computer simulations. Future projects, including the Euclid mission, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope, will advance this work. They aim to reveal how galaxy groups interact with dark matter and how these immense gravitational flows have evolved over billions of years. Laniakea reminds us that we are part of something unimaginably greater. The Milky Way, and our solar system are not drifting aimlessly, but are guided along invisible highways carved by gravity, traveling toward a destination we do not yet fully comprehend. Our true home is this vast structure of the cosmos, and we are all passengers on its endless voyage. Our solar system includes the inner planets, Mercury, Venus, Earth, and Mars, the gas giants, and the dwarf planet Pluto in the Kuiper Belt. While Pluto was once considered the edge of our Sun's kingdom, its domain extends much further. Beyond the Kuiper Belt and the scattered disk lies the Oort cloud, one of the most distant and mysterious structures imagined. It is envisioned as a giant sphere composed not of light or gas, but of frozen bodies like comets and icy debris left over from the solar system's formation. This shell is thought to surround the Sun, marking the very edge of its gravitational influence. The Oort cloud is ancient, having formed during the solar system's infancy billions of years ago. It is believed to contain trillions of frozen objects, each a relic of creation that can be dislodged and sent inward toward the Sun. A question that is rarely asked is what the underside of the Oort cloud is like. It is usually imagined as a vast symmetrical sphere, but its southern half, which dips below the solar system's main orbital plane, could be different from the northern half. It might hold secrets untouched for billions of years, or perhaps relics from other star systems. To comprehend the Oort cloud's sheer size, the astronomical unit AU is used, where 1 AU is the average distance between Earth and the Sun, about 150 million kilometers. The Oort cloud begins at around 2,000 duas AU from the Sun and may extend as far as 100,000 duas AU. For perspective, Pluto orbits at about 40 AU, humanity's most distant spacecraft. Voyager 1, which has been traveling outward since 1977, has passed beyond the edge of the heliosphere. The Sun's protective bubble Voyager 1 is currently about 160 astronomical units from Earth, a distance that has not yet reached the main body of the Oort cloud. From the spacecraft's perspective, the cloud remains a distant region. The scale is so vast that if the Sun and its planets were reduced to the size of a coin, the Oort cloud would extend across an entire city. It represents a frontier of both physical distance and imagination. No telescope has ever directly observed the Oort cloud because it is too faint, diffuse, and distant. Its icy fragments are small and reflect very little sunlight, making it an invisible structure to us. Nevertheless, we know it exists due to the presence of comets, which are icy bodies that enter the inner solar system on highly elongated orbits. Unlike short-period comets, these long-period comets arrive from random directions, with some following sharply tilted paths, and others moving in retrograde motion compared to the planets. Such trajectories can only be explained by their origin in a distant spherical reservoir, the Oort cloud. Some comets appear to originate from the southern half of this icy sphere. Notable examples like Comet Hale-Bopp in 1995 and Comet C 2017 K2, Pan-STARRS, both entered the solar system on steeply inclined paths as if arriving from below. These comets provide indirect evidence that the Oort cloud is a three-dimensional sphere surrounding the Sun, not a flat disk. This spherical symmetry raises a new question. Is the Oort cloud uniform, or does its southern half differ from its northern half? Some scientists believe the southern regions may have unique characteristics. One reason relates to our solar system's position within the Milky Way. The Sun is not situated perfectly in the center of the galactic disk, but rather slightly above it. Consequently, the lower part of the Oort cloud may experience the galaxy's gravitational pull differently. Over billions of years, this uneven force could stretch or compress the southern hemisphere in ways not seen in the north. If this is the case, more comets might travel inward from the southern region, making it a more active area. The Oort cloud is not an undisturbed environment. As the Sun orbits the center of the Milky Way, over more than 200 million years, it encounters other stars. Some pass close enough to gravitationally perturb the Oort cloud, dislodging its icy bodies toward the inner solar system. About 70 years ago, a red dwarf called Schultz's star passed within less than a light year of the Sun. Its proximity was sufficient to affect the Oort cloud, likely dislodging comets, perhaps particularly from its southern half. In approximately 1/300,000 years, another star, Gliese 710, will pass within about 0.06 light years, a flyby that will almost certainly scatter many comets inward. A large number of these may originate from the southern portion of the Oort cloud. Stars are not the only cosmic factors at play. Some scientists speculate that the Oort cloud may also be shaped by dark matter, an unseen substance that constitutes most of the universe's mass. While it does not interact with light, its gravity shapes galaxies. Some models suggest that dense clumps of dark matter may occasionally pass through the outer solar system, especially from less observed directions, such as the south. Such encounters could disturb the Oort cloud and send comets inward in waves. If these showers were large enough, they could potentially cause extinction events on Earth, similar to past impacts. This speculative idea suggests a potential danger associated with the southern region of the Oort cloud, linking it to cycles of life and death on our planet. Another theory suggests that the southern portion of the Oort cloud may contain not just objects native to our solar system, but also interstellar comets. Billions of years ago, during the solar system's early formation, giant planets ejected countless small planetesimals. Some escaped, while others were trapped in the Oort cloud. During this era, the Sun was part of a dense star cluster. It is thought that icy debris from other newborn stars may have been captured by the Sun's gravity. If so, the Oort cloud, especially its southern regions, might contain comets from other star systems. These objects would be chemically distinct, carrying different isotopes, minerals, and volatile elements than comets formed around our Sun. Each would be a source of information from different stellar nurseries. Studying them would be like analyzing material from other stars. The primary challenge is distance, as no spacecraft has approached the Oort cloud and no telescope has observed it. The key to understanding its southern region lies in the comets themselves. Each comet entering the inner solar system provides data from the edge of this region. By charting their trajectories, astronomers can trace their origins. Comets arriving from high southern inclinations offer clues about the southern hemisphere. By analyzing their chemical compositions, scientists can compare comets from the southern and northern regions. New instruments such as the Vera C. Rubin Observatory are expected to discover thousands of new, long-period comets, many originating from the southern sky. Each discovery will help determine if the southern hemisphere differs from the northern one. A future mission to this region may be possible. NASA has considered concepts for an interstellar probe that could travel thousands of astronomical units from the Sun. Such a spacecraft could eventually reach the inner edge of the Oort cloud, where it could measure dust magnetic fields and particle compositions. This would provide the first direct evidence of the cloud's nature. By comparing data from different regions, we could discover if the southern portion of the Oort cloud has features not visible from afar. This would be a journey to the oldest frontier of the solar system, a region where the Sun's influence wanes and galactic forces become dominant. The southern region of the Oort cloud is a frontier where scientific understanding is limited and intersects with speculation. It may contain comets from other stars, be influenced by passing stars, and shaped by dark matter. It could be asymmetrical and a source of future comets. For now, it remains unobserved, but each new comet and future mission brings us closer to understanding it. The Oort cloud's underside represents a boundary of the Sun's influence and may hold keys to understanding fundamental cycles of our solar system and galaxy. At the center of the Milky Way's rotational path lies the galactic core, a massive and ancient structure that serves as the galaxy's gravitational anchor. This region is not empty or static. It is a dynamic, dense, and luminous area containing countless stars, complex magnetic fields, and a central supermassive black hole known as Sagittarius A. Our solar system is in motion within the Milky Way, orbiting the galactic center in a wide, nearly flat path that takes about 225 million years to complete. The last time our solar system was in its current orbital position, dinosaurs inhabited the Earth. This journey is not perfectly smooth, as gravitational forces prevent a uniform orbit. Instead, the solar system oscillates vertically as it travels with a cycle of roughly 30 to 35 million years. Periodically, it crosses the galactic midplane, rises above it, and then sinks below, influenced by the combined gravity of stars, gas clouds, and dark matter. At present, our solar system is located about 25 to 30 light-years above the galactic midplane and is slowly moving downward. This vertical motion, though imperceptible in a single lifetime, is significant as it plays a crucial role in the circulation of material throughout the galaxy. Gas, dust, and entire star systems can move above and below the galactic disk, gradually funneling toward the center through processes that astronomers are just starting to comprehend. If an object were released from our solar system's location to fall toward the galactic center, it would initially pass through the galactic disk. This broad flat area contains most of the stars, nebulae, and dust appearing as the band of the Milky Way in the night sky, where starlight merges into a glow. As the object descended, gravity would intensify, with the pull strengthening as it neared Sagittarius A. Our Sun is approximately 26,000 light-years from the galactic center, making the fall exceptionally long. The object's speed would increase with each light-year it traveled. The fabric of space-time curves inward, creating a steeper descent, akin to sliding down a large invisible funnel. This descent would not be a direct fall. The Milky Way rotates with its inner regions, spinning faster than its outer parts, much like a whirlpool. An object falling from above or below the disk would be drawn into this rotation, causing it to spiral toward the center, rather than moving in a straight line. Its trajectory would take it through regions much denser than our own, where stars are so concentrated the sky would appear intensely bright. The spiral path would lead through the galactic bulge, a dense, round cluster of old reddish stars, where stellar density is hundreds of times higher than near our Sun. During its journey, the object would traverse large, cold, dark molecular clouds where new stars form, move through powerful, invisible magnetic filaments, and experience the turbulent central molecular zone, a site of continuous star formation and destruction. Considering a fall from below the galactic disk is interesting because the galaxy's southern half has historically been studied less than the northern half. For centuries, major observatories were located in the northern hemisphere, providing astronomers with better views of the stars above the disk. This is now changing. New instruments in the southern hemisphere, like the Vista telescope in Chile, are starting to map the southern skies. The Vera C. Rubin Observatory will soon provide highly detailed views of these previously underexplored regions. This will allow the southern path toward the galactic center to be studied with the same level of precision as the northern one for the first time. With continued descent, the object would encounter more extreme conditions. Matter and radiation would grow denser, and magnetic fields would become more tightly structured. The environment would include neutron stars, which are the collapsed cores of massive stars, along with stellar collisions and unseen smaller black holes. At the galaxy's core is Sagittarius A, a supermassive black hole with a mass equivalent to about 3 million suns. It is nearly stationary, and its gravity anchors the galaxy, influencing stellar orbits tens of thousands of light years away. Approaching it means entering a region where light bends, time is altered, and space is distorted. While Sagittarius A is currently calm, evidence suggests it was more active in the past. Astronomers have found that a few million years ago, it produced massive energy jets that blasted into space. The remnants of these eruptions exist today as two large bubble-like structures known as the Fermi bubbles, extending above and below the galactic plane, testifying to the black hole's turbulent history. Near the black hole is the innermost stable circular orbit, an invisible threshold. An object crossing this line can no longer maintain a stable orbit and will fall in. However, most objects are destroyed by tidal forces, radiation, or magnetic storms long before reaching this point. This thought experiment is a serious concept for astronomers. The vertical movements of stars and gas above and below the galactic disk are crucial for understanding the Milky Way's long-term evolution. These movements account for how stars migrate, how gas clouds disperse or condense, and how matter is eventually channeled toward the central black hole. An accumulation of material near Sagittarius A can lead to new energy outbursts capable of altering the galaxy's structure. Therefore, the Milky Way is a dynamic system of colliding and migrating matter, not a static disk of stars in uniform orbits. A similar process of rising, falling, and spiraling inward occurs on a smaller scale within our solar system. A thick dust cloud surrounds the planets, primarily situated along the flat orbital plane called the ecliptic. It was once believed this dust was in a single layer, but infrared space telescopes like IRAS and COBE have shown it exists in multiple layers extending above and below the main plane. While the Sun's gravity pulls this dust inward, the planet's gravity also influences its distribution. Additionally, the Poynting-Robertson drag effect causes the dust to spiral toward the Sun. In their journey, many of these dust particles intersect with Earth's orbit from both above and below the orbital plane. Not all of these dust particles originated in our solar system. Some are interstellar micrometeoroids, which are small fragments of matter from outside our system. They travel on hyperbolic paths, entering the heliosphere from various directions. Data from spacecraft like Ulysses, Galileo, and Cassini indicate a large portion of this dust arrives from the galactic south. Passing through our system from beneath the planetary plane, these interstellar particles are extremely small and fast-striking with significant force despite their size. While most are too small to puncture spacecraft, they can cause cumulative damage over time, such as scratching thermal blankets, blurring lenses, or piercing solar panels. The International Space Station manages this risk seriously, using protective shielding on its modules and adjusting its orientation to reduce exposure during meteor showers. At orbital speeds, even a tiny dust fragment can have a powerful impact. Scientists use instruments like DRAGON's debris-resistive acoustic grid, orbital Navy sensor to study and predict these impacts. This sensor detects dust impacts as they happen, allowing researchers to map the direction and velocity of incoming micrometeoroids. The data confirms that a significant number of these particles originate from the southern sky, impacting from below Earth's orbital plane. Future missions will encounter greater challenges. Spacecraft, such as Solar Orbiter, which travels outside the main planetary plane, are starting to collect dust samples in unique orbits. Missions to the Oort cloud at the edge of our solar system will face different types of micrometeoroids. The study of these particles, particularly those arriving from unconventional angles, shows that our solar system is a dynamic three-dimensional environment where dust and debris are constantly moving, colliding, and spiraling inward, thereby shaping the surrounding cosmic space. The common perception of the universe involves the circular orbits of planets, the elliptical paths of comets, and the sun's gravity maintaining order. This view suggests a system governed by clear orbital rules, with gravity acting as a stabilizing force. However, there may be a more complex and hidden structure. Astronomers and mathematicians are starting to identify what appears to be an underlying architecture of the universe. A subtle network of invisible gravitational pathways. These are not physical structures that can be entered. Invisible even to the most powerful telescopes, these subtle gravitational highways are sculpted by the combined pull of the Sun, the planets, and the Milky Way galaxy. They create natural routes through space, where an object can travel with minimal effort, as if sliding along an unseen current. Much like a river follows the gentle slope of the land, these cosmic pathways are shaped by the delicate balance of gravity, forming the space equivalent of riverbeds. Scientists have long studied similar paths within the ecliptic, the flat plane where planets orbit the Sun. This region contains the Interplanetary Transport Network, a system of invisible paths, partly shaped by Lagrange points. At these specific points, the gravitational pulls of the Sun and a planet cancel each other, creating areas of balance where objects like spacecraft or comets can hover, orbit, or enter controlled chaotic motion. These points function as gateways, forming webs of motion that connect planets, moons, and other celestial bodies. For centuries, however, focus remained on this flat plane of orbits. By exploring the vertical dimension above and below the solar system's disk, mathematicians and astronomers have applied the restricted three-body problem, which examines the gravitational interactions among a star, a planet, and a much smaller object. This reveals that gravity is not a flat surface, but a three-dimensional landscape of gravitational energy with folds, curves, and dips that resemble valleys, ridges, and mountain passes. These gravitational curves create routes across the planetary plane, as well as far above and below it. In these regions, gravitational valleys function as energy-saving lanes, allowing a spacecraft to travel vast distances with minimal fuel by using the natural pull of gravity. This principle is already being applied by missions like NASA's Lucy and the European Space Agency's JUICE, which use these gravitational highways for more efficient travel by navigating the natural contours of space. These invisible corridors may also exist deep beneath the Sun, in areas less affected by large planets, potentially acting as funnels that channel material like asteroids and comets toward the inner solar system. For example, an icy body from the distant Oort cloud could slide inward along one of these lanes, guided gently like a leaf on a stream. The Sun's mass curves space, and when its influence combines with the gravitational pull of the galactic mid-plane, it creates slopes that form low-energy routes in all directions. A spacecraft positioned on one of these lanes beneath the Sun could theoretically be pushed outward on a natural escape trajectory, exiting the solar system with very little fuel. These corridors might have played a role in our origins, as icy bodies and planetesimals in the early solar system could have traveled down these lanes to deliver water ice and minerals to the inner planets. The unusual tilts or elemental compositions of some worlds could be evidence of this ancient vertical infall of debris. However, these pathways can also act as traps, capturing rocks, dust, and artificial fragments in unusual temporary orbits around the Sun, which may explain strange groupings of rocks or dust clouds observed by astronomers. Some of this trapped material could have been suspended for billions of years. Mapping this gravitational architecture is vital for future space exploration, including missions to the Kuiper Belt, interstellar journeys, and strategies for deflecting asteroids. By using these lanes, it may be possible to travel through the solar system with minimal fuel. If other intelligent civilizations exist, they might have already mastered these gravitational highways for travel between star systems. These invisible pathways demonstrate that space is not empty, but is a structured environment with possibilities for understanding our origins, protecting Earth, and traveling to the stars. Beneath the solar system's plane of travel through the Milky Way lies a quiet region of space. Interstellar space is not empty, but contains a faint presence of gas and dust. Our solar system is currently passing through such a formation, which astronomers call the Local Interstellar Cloud, LIC. The LIC is not dense, like clouds on Earth, but is an extremely thin blend of partly charged hydrogen and helium atoms that would be invisible to the human eye. It spans approximately 30 light-years of vast distance that is still small on a galactic scale. The LIC is a fragment within the local bubble, a much larger cavity in the interstellar medium that was created by ancient stellar explosions. The LIC is one of the few wisps of material drifting within this otherwise empty expanse. In the southern direction of the galaxy, beneath the local interstellar cloud, astronomers have found an even less dense region known as the intercloud medium. The galaxy can be compared to a patchwork quilt with dense clouds of gas and dust representing the thick patches where stars form, and the intercloud medium representing the sparse seams between them. This vast expanse of extremely low-density interstellar material is what lies beneath our solar system's current path. For comparison, the local interstellar cloud has a density of about 0.3 atoms per cubic centimeter. While this density is extremely low, it is significant on a cosmic scale. In comparison, regions below the local interstellar cloud, LIC, can have densities of approximately 0.05 atoms per cubic centimeter or less, approaching a near-perfect vacuum. These seemingly minor density variations are consequential as they define the boundary of the heliosphere, our solar system's protective bubble. The heliosphere is formed by the solar wind, a continuous outflow of charged particles from the Sun. The heliopause is the boundary, where the outward pressure of this solar wind is balanced by the pressure of the surrounding interstellar medium. The heliosphere's size is not static. It expands when the solar system moves through a region of lower interstellar density due to reduced external pressure and contracts when it enters a denser region. Consequently, the protective bubble around Earth and the other planets changes in size and shape as it traverses different galactic environments. Current models suggest the solar system is nearing the edge of the local interstellar cloud. If this is correct, it may soon enter one of the less dense regions beyond it. Such a transition would cause the heliosphere to expand, allowing more high-energy cosmic rays from distant stars and galaxies to penetrate deeper into our solar system. This could lead to increased interference with satellite and spacecraft electronics and pose greater health risks to astronauts on long-duration missions. The composition of these nearly undetectable regions is studied by analyzing ultraviolet light from nearby stars. As this light passes through interstellar gas, certain wavelengths are absorbed, creating faint absorption lines in the stellar spectrum. By studying these lines, astronomers can map the density and boundaries of gas clouds. Instruments like the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer, FUSE, have been crucial for this work. Observations of stars south of the galactic plane, such as Alpha Centauri and Altair, allow scientists to trace where the local interstellar cloud gives way to emptier space as the starlight carries information about the medium it has traveled through. These low-density areas originated from supernovae, the explosions of massive stars millions of years ago. These events created large cavities of thin hot gas within the interstellar medium. The merging of several such cavities, likely occurring 10 to 20 million years ago, formed the local bubble, a void approximately 300 light-years in diameter. The local interstellar cloud resides within this bubble, with an even more rarefied region located beneath it. This region consists mainly of a thin, hot plasma of ionized atoms rather than molecules or dust. Future missions venturing south of the heliosphere, such as a proposed interstellar probe or a successor to the Voyager spacecraft, would be the first to directly measure this intercloud medium. This low-density environment is scientifically valuable. The reduced number of particles allows long-range signals, like radio waves, to travel with less scattering and absorption compared to denser areas. Some scientists have proposed that such regions could function as corridors for interstellar communication, allowing a station placed within one to detect faint signals from great distances. The region beneath the local interstellar cloud is a quiet, low-density space created by ancient supernovae. Our solar system is currently moving toward this exceptionally empty region. Paradoxically, studying this void may reveal more about our galaxy than studying the denser clouds. Its emptiness provides a unique context for understanding galactic processes as our solar system continues its journey. Positioned high above and far below the plane of the Milky Way are two immense structures known as the Fermi bubbles, spanning tens of thousands of light-years. These features were discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. Their origin has been a significant topic of astronomical inquiry since their discovery. Each bubble extends approximately 25,000 light-years perpendicular to the galactic disk, a distance comparable to that between Earth and the galactic center. The bubbles are filled with gamma rays, the most energetic form of electromagnetic radiation, which are produced by high-energy cosmic events such as matter accretion by black holes, supernovae, and high-velocity particle collisions. A notable characteristic of the Fermi bubbles is their sharply defined edges, which contrast with the diffuse galactic halo, the vast sphere of stars' dark matter and thin gas surrounding the Milky Way. The bubbles contain high-temperature plasma streams of energetic particles and complex magnetic fields. They are also expanding at a rate of nearly 1,000 kilometers per second. Their cause is not attributed to a nearby supernova or a region of intense star formation. The leading hypothesis suggests they originated from a period of past activity of Sagittarius A, the supermassive black hole at the center of our galaxy. Millions of years ago, this black hole may have accreted large amounts of gas and ejected powerful jets of particles. These jets, directed upward and downward from the galactic center, could have created cavities in the halo, filling them with heated gas and generating gamma rays. The structures we observe today may be the afterglow of this ancient eruption. An alternative theory is that the bubbles were formed by a starburst event, a period of rapid and extensive star formation near the galactic center. The powerful winds of gas and radiation from such an event could have been sufficient to create these structures. Both hypotheses point to a major energetic event in the Milky Way's history that produced two large persistent lobes of energy. The bubbles also have a complex internal structure, including layers that emit X-rays, which were detected by observatories such as Rosat and Erosita. Their sharp edges act as pressure fronts or shock waves, compressing and heating the surrounding halo gas. The Fermi bubbles overlap with other large-scale galactic features, such as the North Polar Spur, highlighting the complexity of the interstellar environment. Furthermore, the bubbles may be unstable, with some studies suggesting they change in size and brightness due to the balance of pressure between their interior and the surrounding gas. The symmetrical shape of the Fermi bubbles points to the galactic core, indicating their energy originated from deep within the galaxy. Astronomers are now investigating if other galaxies, not just the Milky Way, have similar features. Observations of galaxies like Centaurus show large lobes of radio energy that resemble the Fermi bubbles, suggesting that such large-scale outbursts might be a normal phase in the life of spiral galaxies. The Fermi bubbles are invisible to the naked eye. However, gamma-ray telescopes reveal them clearly, showing they cover a vast area of the sky. If human eyes could see gamma rays, these structures would overpower the familiar constellations. The night sky would instead be dominated by two towering pillars of energy above and below the Milky Way, appearing like celestial monuments to a powerful event at our galaxy's core. Long ago, far below the plane of our solar system, beyond comets and cosmic dust, there exists a strange feature. It is not a moving object or a cloud of particles, but an anomaly within the fabric of the universe itself, appearing as a scar on the oldest light ever observed. This feature is found in the cosmic microwave background radiation, or CMB, which is the faint afterglow of the Big Bang that fills the entire sky. Invisible light, the universe is a collection of stars, galaxies, and nebulae. In the microwave spectrum, however, it is defined by this faint, nearly uniform glow across the sky. This uniformity is not perfect, as the CMB contains minute temperature variations of only millionths of a degree. These small fluctuations were the seeds from which galaxies, stars, and planets formed. Among these variations, one region stands out: a large, cold patch located well below the galactic plane in the southern sky. Astronomers call it the CMB cold spot. It is situated in the southern constellation of Eridanus, far below both the Sun's ecliptic path and the disk of the Milky Way. The cold spot is large, spanning nearly 5 degrees of the sky, or about 10 times the width of the full moon. Its most striking characteristic is its temperature, which is approximately 70 microkelvin colder than its surroundings. While this difference is insignificant by everyday standards in cosmology, it represents a major anomaly. This signal is so unusual that it has created both excitement and confusion among scientists. The first indication of this cold region appeared in 2004 from maps of the CMB created by NASA's Wilkinson Microwave Anisotropy Probe, WMAP. In 2013, the European Space Agency's Planck satellite confirmed the anomaly with greater precision. Both missions designed for accurate measurement of the early universe's glow found that this patch of sky was too cold and too large to be explained by random chance. While small fluctuations in the CMB are expected and are in fact necessary for the formation of cosmic structures, the cold spot is an unusually large and deep variation. The probability of such a feature occurring by chance is extremely low. Furthermore, its location in the southern galactic hemisphere, an area with minimal interference from dust or galactic radiation, makes its existence more difficult to dismiss as an observational error. One possible explanation is that the cold spot is a coincidence, a rare quantum fluctuation from the early universe that grew to an unusually large size. While mathematically possible, many researchers find this explanation unsatisfying due to its low probability. Another theory, the supervoid hypothesis, suggests the cold spot is caused by an enormous underdense region of space containing far fewer galaxies than average. As CMB photons pass through such a void, they lose energy through the integrated Sachs-Wolf effect, making them appear cooler. Galaxy surveys have confirmed a void exists in that direction, but it is not large or empty enough to fully account for the observed temperature drop. This explanation is therefore considered incomplete. This has led some scientists to propose more exotic possibilities, such as the cold spot, being the result of a collision between our universe and another during the period of cosmic inflation. If correct, this would not only provide insight into the early universe, but also suggest our universe is part of a larger multiverse. Although there is no solid evidence for this theory, it remains an intriguing possibility because the cold spot consistently appears in all observational data. The cold spot is not the only anomaly. Other unusual features in the CMB, such as strange alignments and statistical imbalances, also appear to be concentrated in the southern sky. While some have suggested these could be observational errors, repeated checks with different instruments and analysis techniques have confirmed they are real. The region around the cold spot is one of the clearest windows to the CMB, with very little interference, which means any unusual findings there are more significant as they cannot be easily attributed to known sources. Today, the cold spot remains one of the most significant puzzles in cosmology. It is not visible to the naked eye and is detectable only as a slight temperature drop in the ancient light of the CMB located below our solar system's plane. It is variously interpreted as a statistical fluke, a cosmic void, or the mark of another universe. The cold spot is a reminder that the universe still holds fundamental mysteries that could be key to understanding our cosmic origins and whether we are alone. Through powerful computer simulations that model the universe's evolution, scientists have concluded that an enormous unseen skeleton of dark matter underlies all visible structures. Dark matter is unlike ordinary matter. It cannot be seen or touched, but is believed to make up most of the universe's mass. It provides the invisible framework that allowed galaxies to form. Without it, the universe would look very different. The distribution of dark matter throughout space is not uniform. The universe is structured as a vast, intricate pattern known as the cosmic web. This structure is composed of massive filaments of invisible matter extending for hundreds of millions of light years. These filaments connect luminous nodes where galaxies form and congregate in large clusters. The cosmic web has a complex and irregular structure. Filaments are dense and thick near massive galaxy clusters with strong gravity, while they are thin and faint in the large empty areas called cosmic voids. Some filaments branch into smaller strands that extend into individual galaxies. The Milky Way galaxy is part of this invisible structure. While the Milky Way appears as a spiral of stars, gas, and dust, it is enveloped in a much larger halo of dark matter. Smaller subfilaments of dark matter may exist within this halo, and could potentially pass through our solar system's region of space. These unobservable filaments might traverse the area above and below the galactic disk, undetected. The existence of dark matter, which cannot be directly observed, is inferred through a natural phenomenon called gravitational lensing. Light typically travels in straight lines, but its path is bent by the gravity of a massive object, similar to how a lens works. Astronomers measure the distortion curvature or warping of light from distant galaxies as it travels to Earth. These small distortions enable the mapping of invisible mass throughout the universe. These maps consistently show web-like filaments of dark matter connecting galaxy clusters. Computer models suggest that our solar system may occasionally pass near one of these dark matter filaments. Smaller, denser concentrations of dark matter, known as subhalos, exist within the Milky Way's larger dark matter halo. If a subhalo were to pass close by, it could subtly affect planetary orbits, disturb comets in the outer solar system, or produce weak lensing effects detectable by sensitive instruments. While direct observation of a local filament has not yet occurred, scientists are making progress. The European Space Agency's Gaia mission, charting the movement of over 1 billion stars, is detecting minor perturbations in star streams. These small disturbances could be evidence of dark matter clumps moving through the galaxy. A dark matter filament near our solar system would be unobservable directly, but could be detected by its gravitational influence on nearby stars and gas clouds. Researchers are investigating whether dark matter filaments affect the trajectories of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. The gravity and potential magnetic effects of denser dark matter strands could slightly alter the paths and energies of these particles. If this hypothesis is confirmed, cosmic ray studies could offer another method for mapping the structure of dark matter filaments. These invisible structures are almost certainly not a cause for concern. Dark matter is extremely thin and diffuse. The densest parts of a filament contain only a few dark matter particles in a volume comparable to a refrigerator, which would be perceived as empty space. However, on a galactic scale, the gravitational pull of dark matter is strong enough to influence star clusters, stellar streams, and the formation of new stars from gas clouds over millions of years. Dark matter filaments can determine the locations of galaxy growth, affect comet clouds like the Oort cloud, and influence the movement of spiral arms. Scientists are developing more sensitive instruments to detect the subtle evidence of dark matter. One such project, the Laser Interferometer Space Antenna, LISA, aims to detect faint gravitational waves that could result from the interaction of dark matter filaments. The CMBS-4 mission will study the cosmic microwave background, the afterglow of the Big Bang. Analyzing minor distortions in this light may reveal dark matter structures from the early universe. If these predictions are accurate, the night sky contains more than just stars. Large formations of dark matter may be moving undetected across the galaxy, influencing the Milky Way's evolution without emitting any light. These are the unobserved components that explain the universe's structural integrity. Rogue planets are isolated objects that travel through the universe. Unlike planets that orbit stars, these worlds drift through the cold, dark, interstellar medium. They lack a host star, a consistent source of heat, and a day-night cycle. They travel continuously through empty space. Some of these planets previously orbited stars in stable paths. Gravitational interactions between large planets or encounters with other stars can eject a planet from its system. The planet is ejected with great force, and travels through interstellar space. Other rogue planets may have formed in isolation from collapsing clouds of gas and dust that were not massive enough to become stars. These planets formed without a host star. The majority of these free-floating planets move within the disk of the Milky Way galaxy. However, some travel on unconventional paths, approaching from above or below the galactic plane at steep angles. A rogue planet, approaching from the galactic north, originates from a region that is not frequently observed by astronomers. This makes its detection more difficult. Detecting these cold, dark, and nearly invisible planets is challenging. Astronomers use methods like gravitational microlensing to find them. When a rogue planet passes in front of a distant star, its gravity bends the starlight. This causes the star to briefly brighten. This temporary brightening indicates the presence of the unseen planet. This technique has led to the discovery of rogue planets of various sizes. From Earth-sized to larger than Jupiter studies indicate that billions of rogue planets may exist in the Milky Way. The number of these planets may exceed the number of stars. The galaxy contains not only stars, but also a large population of unlit, free-floating planets. The question is how some of these planets attain orbits far above or below the galactic disk. The Milky Way's disk is not static. It is dynamic and affected by major galactic events. The gravitational forces during galactic collisions or close passes can eject stars and planets from their typical orbits. Some are ejected into the galactic halo, the region surrounding the disk. Rogue planets might also originate from dwarf galaxies or star clusters that have passed through the Milky Way, leaving behind stars, gas, and planets in multi-star systems. Chaotic gravitational interactions can also eject planets into high-arcing orbits that take them far above the galactic disk before they return. A rogue planet approaching our solar system from the direction of the galactic north would be difficult to detect. Telescopes are primarily focused on the galactic plane or objects within our solar system. A dark object approaching from above the galactic plane would likely go unnoticed. These planets emit very little visible light. Lacking a host star for heat, they emit only faint residual heat from their formation, which is detectable in infrared wavelengths. Powerful instruments like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope possess the sensitivity to detect the faint heat of rogue planets. However, for these telescopes, the search is akin to finding a faint ember in the vast darkness of space. The probability of one of these wandering planets approaching us is very low. Space is exceptionally vast, and our solar system occupies only a small part of the galaxy. Nevertheless, a small chance is not the same as an impossibility. According to scientific models, a rogue planet or a similar object might pass within a few light years of our Sun approximately once every few million years. Such a visitor could cause disruptions without colliding with Earth or any other planet. Its gravity could disturb the Oort cloud, the large sphere of icy comets that surrounds the solar system, sending many of them inward. This could create waves of icy bodies moving into the inner solar system, with some potentially directed toward Earth. Some scientists propose that this is not only a future possibility, but may have also happened in the past. An unconventional theory suggests that the hypothetical Planet 9, a massive world thought to exist beyond Pluto, might not be a native planet. Instead, it could be a rogue planet, captured by the Sun's gravity millions of years ago and pulled into a long, elliptical orbit that keeps it concealed in the far reaches of our solar system. While this theory remains unconfirmed, it suggests that our solar system's history might include encounters with objects from interstellar space. The study of rogue planets also offers broader insights. They function as markers that help map the underlying structure of the Milky Way. By analyzing their movements, astronomers can improve their understanding of the galactic halo, the motion of the galactic disk, and the influence of dark matter. Despite being cold and dark, rogue planets could hold keys to understanding our galaxy's architecture. In the coming years, new wide-field sky surveys, including the European Space Agency's Euclid telescope and the Vera Rubin Observatory, will conduct more thorough searches for these faint objects, including in less observed regions of the sky. Although the night sky appears filled with stars, it may also contain numerous invisible worlds drifting through the cosmos. It is possible that one of these silent objects is currently moving slowly toward us from the darkness. Answers to some of the universe's greatest questions may lie within a type of matter we cannot see. This invisible substance, dark matter, might hold secrets about the universe's fundamental structure. Some scientists theorize that part of this mystery is located in quiet, dark regions beneath the plane of the Milky Way galaxy. To find dark matter, researchers have undertaken significant efforts, including building deep underground laboratories shielded from cosmic radiation, placing telescopes at high altitudes, and using particle accelerators to smash atoms together in hopes of revealing its constituent particles. However, a less explored area may exist just below the Milky Way's plane, where scientists suspect large numbers of unusual invisible particles are moving. The leading candidates for these particles are WIMPs, weakly interacting massive particles, and axions. WIMPs are theorized to be heavy particles that rarely interact with ordinary matter, passing through planets and stars while exerting only a gravitational influence, making them strong candidates for dark matter. In contrast, axions are thought to be extremely light particles, initially proposed to address a problem in quantum chromodynamics. Axions might also account for the universe's hidden mass. Unlike WIMPs, axions could form vast wave-like fields and interact weakly with magnetic fields, giving them distinct properties within galaxies. To envision where these particles might accumulate, consider the Milky Way as a thick, active disk of stars, gas, and radiation, with frequent energetic events such as exploding stars and radiation from newborn stars. Just below the galactic mid-plane, there is a calmer region less affected by this activity. This quiet zone could serve as a gravitational basin where slow-moving particles collect over time, potentially forming thin, extended layers or subtle structures of dark matter below the galactic plane. Computer models of galaxies support this, suggesting dark matter can clump into smaller patterns like streams or rings that move through the galaxy rather than just forming a smooth halo. If one of these streams were to pass near our solar system, it could direct a flow of dark matter particles toward Earth, possibly from below, a trajectory that most current instruments are not designed to detect. Detecting these particles is a significant challenge, which is why scientists have developed experiments like Xenon, Lux Zeppelin, and ADMX. These instruments are built to capture extremely rare events, such as a WIMP striking an atomic nucleus or an axion converting into a faint photon within a strong magnetic field. Earth's own movement complicates detection, as its spin and orbit cause the angle of incoming dark matter particles to change, leading to seasonal and directional variations in detection rates. Researchers are now exploring whether Earth's position relative to the galactic midplane might also affect these variations, especially if particles are arriving from below. Our solar system is not situated exactly on the Milky Way's midplane, but is currently About 20 light-years above it. It moves through the disk in an oscillating pattern that completes a cycle roughly every 60 million years. At present, our solar system is slowly descending toward the region below the galactic plane, which could bring us into areas with different or higher concentrations of dark matter. Some scientists believe this vertical motion could explain puzzling data from certain experiments. For instance, the Dama Libra detector has observed unusual seasonal patterns that could align with the idea of Earth moving through denser streams of dark matter located beneath the galactic plane. In some models, axions might form large filaments or sheets. If these structures exist below the Milky Way's plane, they could intersect Earth's path at specific angles, generating bursts of detectable particles at certain times. Beyond current detectors, a new generation of tools is emerging. Scientists are developing quantum technologies, such as atom interferometers, which measure tiny disturbances using the motion of atoms, and superconducting microwave cavities, which could detect axion-like particles with greater precision. One novel proposal is to aim these instruments downward, below the galactic disk, toward the southern celestial hemisphere. This approach could enable the detection of particles that have so far gone unnoticed. The success of these instruments could reveal more about dark matter and uncover hidden aspects of our galaxy's structure. We might find that dark matter is not a uniform substance, but is organized into an invisible network of filaments and streams. This structure could influence how galaxies form and evolve, and humanity is just beginning to investigate this cosmic mystery. The common mental image of the universe is often one of an orderly disk, where planets, moons, and comets follow smooth, predictable orbits around the Sun. Objects in the solar system appear to be organized on a single plane. The Earth's orbital path around the Sun, known as the ecliptic, is a primary example of this apparent order. This plane serves as a line of reference suggesting symmetry and structure. However, this apparent order is superficial. Beyond it exists a less ordered and less studied region characterized by ancient fragments, comets on unexpected trajectories, and complex gravitational forces that are difficult to model. This region can be considered a dark, dynamic, and largely unexplored part of the solar system. The most well-known objects in this region are asteroids and comets. While most have orbits close to the ecliptic plane, some do not follow this pattern. Certain objects, particularly those originating from the Oort cloud, have highly inclined orbits. Halley's Comet is a notable example. Unlike the planets, which share a common orbital direction, Halley's Comet follows a highly inclined orbit in a retrograde motion. Its path passes below the ecliptic before ascending above it. Other icy bodies, including centaurs and damocloids, exhibit similar behavior with inclined orbits that cross below the ecliptic. Many long-period comets with orbital periods of thousands or millions of years follow trajectories with such high inclinations that they seem nearly random from a side-on perspective. Their paths appear as steep descents from south of the ecliptic. They pass the Sun and then recede into the outer solar system. These brief appearances indicate the presence of significant gravitational forces in the outer solar system. Beyond the Kuiper belt is the scattered disk, a large region of icy bodies and fragments, many of which are located at significant distances south of the ecliptic plane. Some scientists propose that their unusual orbital alignments may have a common cause, suggesting a large undiscovered planet, theorized as Planet 9, may exist. This hypothetical planet could be exerting gravitational influence on these distant objects, causing their highly inclined orbits. If this theory is correct, the regions south of the ecliptic may be shaped by the gravity of this planet. Gravitational effects are not the only factor. The solar system itself is in motion, traveling through the galaxy. This movement creates a gravitational effect in the interstellar medium. The solar system's galactic trajectory is slightly inclined upward relative to the ecliptic plane. Consequently, material located south of the ecliptic may be more susceptible to disturbances, inward displacement, or gravitational effects from the galaxy. The Sun's magnetic field also plays a significant role. This field extends outward in a spiral pattern shaped by the Sun's rotation, forming a structure called the heliospheric current sheet. It is a vast, undulating surface of charged particles that extends above and below the ecliptic. This sheet reaches billions of kilometers into space, with sections that curve below the ecliptic plane. It carries solar particles and magnetic fields, creating a complex and dynamic magnetic environment. These magnetic forces deflect cosmic rays, scatter dust grains, and trap particles from interstellar space. Spacecraft have provided data about this region. The Ulysses probe, launched in the 1990s to study the Sun's polar regions, also provided information on the behavior of plasma flows and magnetic fields at high solar latitudes away from the ecliptic. As Voyager 2 exited the heliosphere, it crossed just south of the ecliptic and detected unusual particle streams and shock waves. These findings suggested that the region south of the ecliptic is not a direct mirror of the region to the north and may be structured differently. Some near-Earth asteroids also indicate this structural complexity. The asteroid 3200 Phaethon, for instance, has a highly elliptical orbit that crosses below the ecliptic plane. Because astronomical surveys often focus on the ecliptic, where most objects are expected, many objects with similarly inclined orbits may remain undiscovered. Furthermore, the zodiacal cloud, a faint band of dust from asteroids and comets, is not confined to a thin plane, but extends both north and south of the ecliptic, as revealed by infrared telescopes like IRAS and WISE. The dust south of the ecliptic scatters sunlight, which it re-emits as infrared radiation. These telescopes have mapped this dust distribution, revealing its motion is influenced by gravity, solar wind, and magnetic forces. The region below the ecliptic is not empty, but contains a complex environment. This area is characterized by objects with highly inclined orbits, such as comets and other fragments, as well as by magnetic fields and galactic influences. This region is distinct from the space north of the ecliptic and exhibits dynamic activity. It is a region where comets travel on steep trajectories. A hypothetical planet may exert gravitational pulls, and the combined forces of the Sun and the galaxy create complex structures that are just beginning to be understood. Far below the galactic midplane, in low-density regions of space, primordial black holes may exist. These are a theoretical type of object. Unlike stellar black holes, which are formed from the collapse of massive stars, primordial black holes are not of stellar origin. They are theorized to have formed from density fluctuations in the early universe. Primordial black holes, or PBHs, can have a wide range of masses, some much smaller than stellar black holes, with masses comparable to an asteroid or a mountain. They are considered a candidate for dark matter. As a theoretical construct, they are difficult to detect because they do not emit or reflect light. If they exist, they may be located south of the galactic disk. Scientists propose that these black holes were created immediately following the Big Bang, within the first fraction of a second of the universe's existence. During this period, the universe experienced significant density fluctuations, and some of these dense regions could have collapsed directly to form black holes. The mass of these primordial black holes would depend on the scale of the initial density fluctuations, allowing for a wide range of possible sizes from subatomic to thousands of solar masses. They are considered remnants from the period before the formation of stars, planets, and galaxies. The reason scientists anticipate finding PBHs below the galactic midplane relates to the gravitational dynamics of the galaxy. Objects such as dark matter stars and black holes orbit the galactic center while also oscillating vertically, moving above and below the galactic plane due to the galaxy's gravitational pull. The Sun also exhibits this vertical motion crossing the midplane approximately every 60 million years. Primordial black holes would likely follow similar orbits. This motion would periodically take them into the region south of the galactic plane, an area with lower densities of gas clouds and stars. This results in less observational interference, which facilitates the detection of the subtle gravitational effects of a PBH. Although they do not emit light, they warp the path of light that passes near them. The technique of gravitational microlensing is used for detection. This occurs when a PBH passes in front of a distant star, causing a temporary magnification of the star's light. Surveys such as OGLE and the forthcoming Vera C. Rubin Observatory monitor the sky for these transient brightening events. The low-density fields south of the galactic plane are considered ideal locations for such searches. Gravitational lensing is not the only potential indicator of their presence. If a primordial black hole were to pass near our solar system, it would not only bend the light from distant stars, but its gravity could also leave subtle imprints on asteroid orbits, alter a spacecraft's trajectory, or even disturb the tenuous structure of dark matter. Detecting such effects would necessitate highly precise models of the Sun's movement and the orbits within our solar system. These signs could reveal phenomena that are otherwise invisible. Another potential clue involves gamma-ray signals. According to Stephen Hawking's theory, black holes can evaporate over time by emitting faint radiation, a quantum effect known as Hawking radiation. If primordial black holes are evaporating, they could be emitting weak gamma-ray signals. The southern galactic hemisphere, being less crowded and quieter than the northern hemisphere, provides an ideal vantage point for searching for these faint energy signatures. Some scientists propose that certain unexplained gravitational waves detected by LIGO and Virgo might have originated from the collision of two primordial black holes. If these black holes tend to congregate in low-density regions, the area beneath the galaxy could be a more probable location for such collisions. In that case, the echoes of their mergers would propagate through the universe as faint vibrations, serving as the sole evidence of these unobservable events. If primordial black holes constitute even a small fraction of dark matter, Earth might occasionally pass through streams of them. During its orbit around the Milky Way, our planet is currently moving downward toward the southern side of the galaxy, which suggests we may be approaching a region containing hidden gravitational disturbances. While we may never capture an image of a primordial black hole, and they might remain unseen, their presence could still be inferred from the bending of starlight's slight orbital perturbations, or the faint ripples in space-time. Deep below our galaxy, these ancient objects may continue to drift as they have for billions of years, silent witnesses to the universe's origin. High-energy cosmic rays frequently arrive from above, moving toward Earth like invisible projectiles from the far reaches of the universe. Although the night sky appears serene, with stable stars and planets in orbit, space is an active environment filled with unseen particles. These particles are known as cosmic rays. Despite their name, cosmic rays are not light. but are instead composed of tiny particles, primarily protons with some heavier atomic nuclei and a smaller number of electrons that possess immense energy. They travel through space at nearly the speed of light. Some cosmic rays are generated in violent supernova explosions. Others may originate from less understood sources, such as galactic centers or other powerful cosmic events. A significant number of them appear to originate from above the ecliptic plane, the flat plane in which the planets orbit the Sun. The reason for this distribution is not yet solved, but scientists believe it is related to the interaction between our galaxy's magnetic fields, the Sun's magnetic forces, and the heliosphere, which is the large protective bubble surrounding our solar system. The heliosphere is formed by the solar wind, a continuous stream of charged particles from the Sun, and the Sun's magnetic fields. This barrier does not block all cosmic rays, but does influence their paths. As these high-speed particles approach from interstellar space, they interact with the solar wind and magnetic fields. The shield's strength varies. During a solar minimum, when the Sun's activity is low, the shield weakens, allowing more cosmic rays to enter the inner solar system, particularly from the Sun's northern direction. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, have explored this boundary. Voyager 1, upon crossing the northern edge of the heliosphere, detected a significant increase in cosmic rays, indicating it had moved beyond the Sun's protective influence and into the direct stream of galactic radiation. The observation that many rays arrive from above could suggest that our solar system is moving through a cosmic headwind, or that the galactic magnetic fields are structured to channel radiation toward us. On Earth, scientists use various instruments to study these particles. Balloons launched over Antarctica and ground-based detectors measure cosmic rays entering our atmosphere. They have determined that Earth's poles receive a higher flux of these particles because both Earth's and the Sun's magnetic fields guide charged particles toward these regions. When cosmic rays collide with atmospheric atoms, they produce the aurorae, luminous displays of green, red, and violet light in the polar skies. Among all cosmic rays, ultra-high energy cosmic rays are the most perplexing to scientists. These particles carry more energy than anything created in Earth's most powerful particle accelerators, in some cases millions of times more. Their exact origins are unknown, though many appear to come from above the plane of the Milky Way. Some scientists theorize they could be produced near supermassive black holes in galactic centers or during massive explosions called gamma-ray bursts, while others acknowledge they may represent a new phenomenon. Large-scale projects have been established to investigate this mystery. The Pierre Auger Observatory in Argentina uses a vast array of detectors to capture these rare particles. In orbit, the Alpha Magnetic Spectrometer on the International Space Station maps cosmic rays with high precision. This instrument has detected an unusual excess of positrons, the antimatter counterparts of electrons, arriving from above the ecliptic plane. This discovery has led to theories such as the annihilation of dark matter or the existence of undiscovered cosmic sources. Cosmic rays are both a subject of scientific wonder and a hazard. They can penetrate spacecraft, damage electronics, and pose a risk to astronauts. While Earth's atmosphere and magnetic field provide protection, the danger from this radiation increases significantly in deep space. For future missions to the Moon, Mars, and beyond, this invisible radiation is a major challenge, and engineers are designing improved spacecraft and shielding based on cosmic ray patterns. Ultimately, cosmic rays act as messengers from the cosmos, carrying information about explosions, black holes, and potentially unknown forces reminding us that space is a dynamic and energetic environment. Physicists have long pursued the theoretical concept of the magnetic monopole, a particle whose discovery would revolutionize our understanding of electromagnetism. A standard magnet always possesses both a north and a south pole, regardless of how many times it is divided. A monopole, by contrast, would have only a single magnetic pole, either north or south. Although never directly observed, the existence of monopoles is a serious consideration in advanced physical theories, appearing naturally in grand unified theories, GUTS, and certain versions of string theory. These frameworks suggest that monopoles may be real, but extremely difficult to detect. A potential search location is in the quiet regions of space, below the sun's path, away from dense matter and turbulent magnetic activity. Monopoles are believed to be exceedingly rare and may have been created in the first moments after the Big Bang, similarly to primordial black holes. If they exist, they would be incredibly massive, possibly thousands of times heavier than a proton, and would therefore move slowly through space. Unlike cosmic rays, they would drift along the galaxy's magnetic field lines. The space below the Milky Way's central plane is calmer, with fewer stars, less plasma, and reduced magnetic interference from stellar explosions, radio bursts, and solar winds. In these zones, the galaxy's coherent magnetic fields are more prominent. If monopoles exist, they are most likely to follow these fields, making this an ideal region for astronomers to search for them. The galaxy's magnetic field can be visualized as a complex network of lines. The southern galactic region may offer a less turbulent magnetic environment, making it a focus for scientific observation. Instruments such as the Ice Cube detector in Antarctica and the Antares telescope in the Mediterranean Sea are designed to detect magnetic monopoles. By identifying unique energy tracks they would leave in ice or water. To date, no monopoles have been detected. Some physicists propose that the search for monopoles would be more effective in space, particularly beyond the sun's magnetic field, where its turbulence would not obscure faint signals. A spacecraft positioned below the ecliptic plane with a view toward the galactic south pole would be ideally situated to detect a slow-moving monopole. An alternative detection method utilizes superconducting loops, which are rings of material that conduct electricity with no resistance. A magnetic monopole passing through one of these loops would induce a lasting change in the electrical current, serving as a definitive signal. Future robotic missions could deploy these loops in the magnetically calmer southern regions of the galaxy to scan for such disturbances. Researchers also theorize that monopoles could be temporarily captured by planetary magnetic fields or in Earth's magnetotail to be released during geomagnetic storms. However, in interplanetary space, especially below the solar system's orbital plane, they could drift freely, leaving subtle evidence for detection. Consequently, future deep space missions may be equipped with sensitive magnetometers to detect the faint magnetic signature of such a particle. The existence of magnetic monopoles is significant because their discovery would validate theoretical physics predictions made over the last 50 years. Furthermore, monopoles could explain why electric charge is quantized, meaning it exists in discrete uniform units. For example, every electron possesses the same negative charge. This uniformity could be a direct consequence of the existence of magnetic monopoles. These particles could be fundamental to developing a unified theory of nature's forces, including gravity, electromagnetism, and the nuclear forces. Although none have been found, the search for magnetic monopoles continues, particularly in the magnetically quiet southern region of the galaxy. The discovery of this particle could be a key to a more complete understanding of the universe. Neutral hydrogen is a common but subtle component of the universe. It forms a vast invisible reservoir of gas located beneath the main disk of the Milky Way galaxy. Unlike stars, neutral hydrogen does not emit visible light. Instead, it faintly emits radio waves at a frequency of 1420 MHz. Known as Hi, neutral hydrogen is the simplest atom consisting of one proton and one electron. While individual atoms are undetectable, large clouds of them emit radio waves at a specific wavelength of 21 centimeters. This 21 centimeter line signal is a crucial astronomical tool for mapping the structure and motion of gas in the galaxy, including in areas obscured from optical telescopes. Significant discoveries have been made below the galactic midplane, an area characterized by colder, calmer, and more pristine conditions. Radio surveys like Hi4Pi and Galahai showed that the hydrogen is not uniformly distributed, but is instead organized into vast layered clouds extending for thousands of light years, often in wave-like patterns. These clouds are dynamic, drifting and changing shape under the influence of galactic rotation and gravity. Some of these gas formations contribute to the galactic warp. The Milky Way's disk is not perfectly flat, but is bent, dipping down on one side and up on the other. The solar system is moving downward into this warp toward a dense hydrogen region in the southern sky. This is significant because neutral hydrogen is the primary material for star formation. By studying these gas layers beneath the galactic disk, astronomers can observe the early stages of stellar evolution, particularly in quiet, low metallicity areas where ancient cosmic processes are preserved. These clouds also serve as a record of the galaxy's history. For instance, some hydrogen streams below the disk are remnants of past galactic collisions where gas from smaller galaxies like the Sagittarius Dwarf or the Magellanic System was stripped away by the Milky Way's gravity. These streams move independently, colliding with the galactic halo and creating shock waves that can either trigger or inhibit star formation. High-velocity clouds are another mystery. These are large masses of neutral hydrogen moving at speeds inconsistent with the galaxy's normal rotation. Their origins are debated with possibilities, including remnants of past collisions, material ejected from stellar explosions falling back, or gas being accreted from the intergalactic cosmic web. The Smith Cloud is a prominent example. This large cloud of neutral hydrogen is on a collision course with the Milky Way and is expected to trigger a significant burst of star formation in the southern galactic hemisphere in about 40 million years. Even before impact, its shock waves provide valuable information about gas dynamics in deep space. Future instruments, particularly the Square Kilometre Array, will enable detailed three-dimensional mapping of these hydrogen layers. This will allow astronomers to track their motion density and interactions with cosmic rays and magnetic fields. Beneath the visible stars and nebulae lies a hidden realm of neutral hydrogen. Its radio emissions contain information about cosmic creation, collisions, and renewal. Neutral hydrogen is a fundamental component of galaxies, serving as the material for starbirth and a record of galactic history. Space is filled with high-energy particles, such as cosmic rays, neutrinos, and ions that travel in all directions, though their distribution is not always uniform. This uneven flow is known as directional anisotropy. Scientists have observed that particles tend to arrive from certain directions more than others. A notable portion of this particle flow appears to originate from below the solar system's orbital plane. Anisotropy refers to this directional unevenness in the arrival of particles. Instruments like the IceCube Neutrino Observatory and satellite-based detectors like PAMELA and AMS-RO2 have consistently measured slight variations, excesses, and deficits in the number of incoming particles from different regions of the sky. Sky maps of this data reveal a pattern where some of the highest energy particles seem to originate from southern galactic latitudes below the galactic plane. This directional bias is statistically significant and has been observed consistently over many years. This consistency indicates that the phenomenon is a genuine feature of the local galactic environment, not an instrumental artifact or an effect of Earth's magnetic field. One potential explanation for this directional preference involves galactic magnetic fields. These fields, potentially denser in the southern galactic hemisphere, due to remnants of supernova shockwaves or other plasma structures, could guide or deflect particles toward the solar system. The Milky Way's history of galactic collisions offers another possible explanation. Over billions of years, our galaxy has absorbed smaller galaxies, leaving streams of stars, gas, and dark matter beneath the galactic plane. If these remnants contain active black holes, collapsed cores, or dense dark matter clumps, they could serve as powerful particle accelerators, sending high-energy particles toward Earth and creating the observed anisotropy. The movement of our solar system through the galaxy also contributes to this effect. The solar system is currently traveling downward through the galactic plane toward the southern sky. This motion causes a kinetic frame shift that makes incoming particles from below seem more energetic, similar to how driving into a storm makes raindrops appear to hit harder from the front. This phenomenon, called Compton-Getting anisotropy, enhances directional differences and allows scientists to separate genuine particle flows from observational biases. By integrating long-term measurements from instruments in both hemispheres, researchers have started to create three-dimensional maps of the particle flows surrounding the solar system. These maps indicate that the space below us is considerably more active than previously understood. Furthermore, these particle anisotropies appear to correspond with other signals, such as gamma-ray gradients from the Fermi Gamma-Ray Space Telescope and neutrino bursts from IceCube. Numerous high-energy phenomena seem more frequent or intense in the southern sky below the galactic plane. This raises the question of whether these are coincidences or evidence of hidden sources like active remnants, magnetic funnels, or unknown astrophysical structures. Understanding these directional flows is important for improving space weather models, which are vital for future deep space missions. It might also reveal the distribution of matter and energy in galactic regions that are difficult to observe and could suggest exotic physics, from dark matter decay to undiscovered cosmic accelerators. While most telescopes observe the sky above the space below, emits particles that carry information about movement structure and unseen forces. While tides are often associated with the rise and fall of oceans caused by the moon or the stretching of stars near black holes, gravity also stretches space over vast distances, affecting stars, clouds, and entire galactic disks. In the southern parts of the Milky Way below the solar system, tidal forces from massive structures are subtly changing how stars move, how the solar system drifts, and perhaps the overall shape of the galaxy. The Milky Way is not a static flat disk. It ripples in response to gravitational influences from within and beyond. A primary influence is the Sagittarius dwarf spheroidal galaxy, a small satellite being absorbed by our galaxy. Its tilted elliptical orbit passes through the Milky Way's disk, creating ripples. These disturbances are most significant below the galactic plane, where Sagittarius leaves behind streams of stars, gas, and dark matter. Its gravity stretches the lower half of the Milky Way, pulling on stars, including the Sun, and affecting the distribution of dark matter. Other satellites, such as the large and small Magellanic Clouds, orbit below the southern disk, and their combined gravity drags dark matter and bends the Milky Way's outer ring, forming a gravitational wake. This uneven pull generates vertical waves through the stars and gas, a motion sometimes known as galactic seismology. Recent data from the Gaia satellite, which maps the positions and motions of over 1 billion stars, confirms that these vertical waves extend over thousands of light-years, showing that the disk is vibrating from past tidal impacts from below. These tidal forces may also impact life on Earth. Some researchers propose that as the solar system moves through the galactic plane, in a cycle of roughly 60 to 70 million years, it travels through denser areas of cosmic dust or experiences more comet activity, which could coincide with mass extinction events and suggest a link between galactic tides and Earth's history. The southern part of the Milky Way, pulled by tidal forces, bends differently than the northern half. These forces reshape the galaxy cluster. Dark matter create ripples in gas clouds and shift stars. The solar system is also involved in this process. The vertical region below the galactic plane is not empty, but contains invisible forces, unseen structures, and the common perception of the universe involves planets in circular orbits, comets moving through space, and numerous stars